Good morning, everybody, and welcome to today's webinar. My name is Cheryl Jennison DeProza, and today I'm joined by Hayden Lipier and Andy Chan, and we're going to be talking about smart digital wireless technologies. But before we get into that, just a few items of housekeeping. This webinar is being recorded and will be available for on-demand viewing sometime within about 1 to 2 weeks after today. So if you want to refresh it or if you want to direct a colleague to it, you will be able to come back to it in about 1 to 2 weeks. It'll be available at shure.com/training. And then second of all, as we go through the session today and you have any questions, please feel free to type those in. You should see a little question pane somewhere probably on the upper right-hand corner of your screen. If you don't see an area where you can enter in questions, look for a small gray toolbar with an orange box with a white arrow in it. Click on that, and that will maximize your question pane. As I said, we will get to those at the end of the session, so type in any questions you have, but please be patient. We will do those at the end. That wraps up all the boring housekeeping stuff. Let's get into the good stuff. Take it away, gentlemen.
Thanks very much, Cheryl. So the webinar today is going to cover smart technologies integrated into Shure's digital wireless microphone systems operating in the UHF, DECT, and 2.4 GHz bands. So the topics covered will give audio engineers and AV designers a deeper understanding of how each product works, knowledge that helps to ensure our wireless microphone systems are correctly specified and configured for a given application. So the specific systems we're going to cover today are GLX-D and GLX-D Advanced, which operate in the 2.4 GHz range. We're going to look at Microflex Wireless, which operates at the 1.9 GHz DECT range. And then we're also going to talk about a few predominantly UHF-based systems, so QLX-D, ULX-D, and Axion Digital. But before we get into talking about the specifics of each of those products, I think it's useful to begin by talking about a few common features to all of these digital wireless systems. So performance features that are common include 24-bit digital audio that delivers incredibly clear and accurate reproduction of any source material. We have a really wide frequency range, right up to 20 kilohertz with a flat response. Very wide dynamic range through to system analog and digital outputs where they're available. Very easy pairing of transmitters and receivers. The way in which that works is a little bit different depending on the system, but we're going to talk about that. We also have encryption on most of these systems. So AES 256 for QLX-D, ULX-D, Axion Digital, and MXW. GLX-D does not use AES 256 encryption, but there is a proprietary codec there that we're going to talk about. We also have advanced power management featuring in-transmitter recharging options, and across the board, durable hardware construction with all metal transmitters and rack-mountable receivers. So what do all these common performance features mean? Well, it means that all of these systems are easy to configure and use. They're all extremely durable and reliable. And perhaps most importantly, they all sound great. Indeed, one of the key advantages of digital wireless systems over analog wireless is that audio quality is not directly influenced by the quality of the RF link. But we'll talk more on that later. Before we get into systems, there are two key features here that are unique to digital wireless, and that's encryption and gain ranging. So let's take a look at those first. In Shure's older generation of UHF analog wireless microphone systems, we had tone key squelch, which prevented the Shure receiver from demodulating non-Shure transmitters. But there was no real protection against other unknown receivers demodulating the analog wireless microphone signal. This is because the modulation scheme was FM, and while there was some proprietary optimization of the signal in terms of EQ and companding, etc., ultimately any FM receiver could be made to demodulate that wireless mic signal. Today, all Shure digital wireless products feature some form of signal security to prevent demodulation of the audio transmitted by an unknown or unintended receiver. A key benefit of developing a digital system is that the methods by which transmitted audio may be secured and protected is quite sophisticated. And as I just mentioned, most of Shure's digital wireless systems employ AES 256 encryption. So AES 256 is a known and really robust algorithm that encrypts the data with a multi-bit key. Shure have implemented a counter mode keystream ciphering method to facilitate bit-by-bit encryption at a very low latency overhead. In the UHF systems, so QLX-D, ULX-D, and Axion Digital, when encryption is enabled, a new multi-bit encryption key is generated each time the transmitter is synced via IR to the receiver. In the DECT-based Microflex wireless system, a new key is generated every time a microphone is linked to an APT, and then that key is refreshed each time the transmitter is removed from the network charger. Now, the exception here is GLX-D, which does not use AES-256 or any other official form of encryption. However, GLX-D does feature a proprietary frequency hopping transmission scheme, and in practice, this does provide some form of security, as you can't really make another receiver tune into to a GLX-D transmitter and demodulate that audio. Okay, moving on, I'd like to quickly talk about gain ranging, as this technology is incorporated into ULX-D, QLX-D, Axion Digital, and GLX-D. So Shure's gain ranging technology enables system dynamic range performance in excess of 100 dB A-weighted through to analog outputs and 130 dB A-weighted through to digital outputs for the systems that feature Dante. So this wide dynamic range, it allows transmitters to accept virtually any input source, practically guaranteeing that even very strong signals, such as those from an electric guitar, for example, will not clip. Furthermore, the noise floor from a very weak input, such as that from a low sensitivity lavalier mic, for example, will be well above the wireless system noise floor. So how does this work? Well, the audio input to the transmitter is Y-split and routed through a low-gain amplifier, which is sent to side 1 of a 2-channel ADC, and also to a high-gain amplifier, which is sent to side 2 of that ADC. So ADC 1, or the low-gain side, is noisier, but it has a higher clipping point. The high-gain side, or ADC 2, is quieter, but it has a lower clipping point. Now, proprietary DSP in the transmitter makes a decision on which audio stream is transmitted based on the level of the input signal. This DSP ensures that audio does not clip and the signal-to-noise ratio remains optimal, regardless of the input. So due to the high quality of Shure's DSP engineering, the process remains acoustically transparent so long as the microphone cartridge isn't overloaded acoustically or the transmitter input is not overloaded electronically. Some gain control is still provided at the transmitter in the form of a gain offset, which is applied in addition to any gain settings at the receiver. So the offset feature just allows the engineer to increase the level of a body pack used with the lavalier mic, for example, to offset the gain difference between a body pack and a handheld transmitter, allowing the engineer to match those levels if you're in a situation where you've got, say, a handheld and a lavalier both tuned into the same receiver channel, and you're going to alternate using those throughout a show. So the beauty of gain ranging is that it's designed to be completely transparent. It does not introduce the artifacts typical of standard dynamics processing employed in the analog wireless microphone systems. And what's really smart about this is that it's removed the need for the engineer to carefully calibrate the gain setting at the transmitter. So the concept of maximizing deviation, which was quite important in analog systems, is no longer a concern with Shure's digital wireless microphone systems. I'd also like to talk a little bit about interference detection, or what's better referred to as error detection in digital systems. So why is error detection so important? Well, unless some form of error detection is incorporated into the digitally transmitted bitstream, the receiver will have no idea if an error has occurred, and this would impact the effectiveness of the muting operation in the presence of interference. So to be suitable for implementation in an audio system, an error detection scheme must be designed for high accuracy, minimum latency, and maximum spectral efficiency. The error detection system that Shure have incorporated is a proprietary algorithm, but it's sort of based on the cyclic redundancy check method, or CRC, which does meet these three criteria and is able to detect about 99.9% of transmission errors. So as demonstrated in this slide, CRC works by performing repetitive binary division on small blocks of data and checking for remainders. So the remainders of each block are transmitted along with the audio signal. This repetitive binary division process is then repeated at the receiver on the same small blocks of data, where the remainders calculated are divided by those remainder values sent by the transmitter. Now, if the result of that division is 0, then no errors are present in that block of data. And of course, if it's not 0, then there is some amount of error. Depending on the severity of the bit error, various concealment, attenuation, or muting algorithms are then deployed. In single carrier systems, like ULX-D, for example, if errors are detected by the receiver, a proprietary algorithm will control the muting operation depending on the extent to which errors are detected. In Axion Digital, depending on how the system is configured, the detection of errors may activate the frequency avoidance process. In spread spectrum systems such as GLX-D and Microflex wireless, error detection is so effective that the system will hop to a new carrier frequency before any audible interference is perceived. So extremely smart technology deployed in these digital systems, and the error detection that we have is fantastic. Okay, so now I'm going to jump in and talk a little bit about specific product lines, starting with GLX-D and GLX-D Advanced. So as I mentioned earlier, these systems operate in the 2.4 GHz ISM bands, which range from 2.4 gig up to 2.4835. So the main disadvantages of using this range are that they're also used for many other wireless services, the biggest of which is Wi-Fi. So heavy RF traffic in this band can adversely affect the performance of GLX-D. Wi-Fi traffic can be unpredictable, and bursts of data can cause abrupt, unexpected interference on your wireless microphone systems. Symptoms of this effect can be short transmission range. You can have a frequent loss of signal, inability to operate multiple systems at the same time. Right, so they're the main challenges when designing a system to operate in this range. There are, fortunately, a couple of key advantages to using the range. The first one is that there is no license required in any country around the world to operate a wireless microphone at 2.4 gigahertz. So that's especially important for people that are traveling with their systems and they don't want the headache of trying to apply for licenses in different countries. The other key advantage is that there is no risk of interference from any local television stations, as television stations don't operate in this range at all. So they're two pretty key advantages. Now, one thing that's important is that when designing a wireless microphone system to operate in an interference-limited environment like the 2.4 gigahertz range, it's really important to find the proper balance between the number of compatible channels that you're after and stable coexistence with interference. Because of this, GLX-D was specifically designed to provide great reliability within the 2.4 gigahertz range in the presence of these other interfering devices as a priority over maximizing channel count. So that's something key to remember with GLX-D. So we'll move on now to talk a little bit about the transmission scheme. So GLX-D features several smart technologies to compensate for the spectrum congestion at 2.4 gig. So each channel of GLX-D is composed of a hop set of 6 possible frequencies located above, below, and within the gaps relative to Wi-Fi channels 1, 6, and 11. And the cleanest 3 frequencies in the hop set are used to transmit the signal. So yes, you heard that right. There are 3 frequencies occupied to transmit the audio signal from each GLX-D transmitter. GLX-D actually provides some redundancy by repeating the most important information such that one frequency can be taken out completely by interference without interruption to the demodulated audio. So if interference occurs on frequency 1, the key audio data may be recovered from either frequencies 2 or 3. On top of this, depending on the group that's used, each channel may have multiple dedicated backup frequencies available to work around interference. So this is a frequency agile system. If one of these 3 initial transmit frequencies experiences interference, a bidirectional data link between transmitter and receiver will allow the system to dynamically hop from one of the allocated spares. Before doing so, thankfully, GLX-D will already know which of the backup frequencies is the best one to use, as the system continuously scans during usage to rank all frequencies in terms of their noise floor level. So this frequency hopping interference avoidance process it's automatic, it's reliable, it's stable, and most importantly, it's acoustically transparent. Now, in terms of hardware, just another nice feature is the GLX-D 4R, the rack mount receiver. It does feature 2 discrete receive sections for true diversity performance. So that's a real advantage, especially at this price point, to have a true diversity system. Now, I did mention earlier that it depends on which group that you're operating in. So, Group 3, for example, does not include backup frequencies, as this is only recommended for controlled Wi-Fi environments, and that's so you can get a maximum channel count out of the system. Group 2 is what I've been talking about here. That's the default, where you have 3 transmit and 3 backup frequencies per channel. So everything's a little bit different. Group 1, it has a different latency setting. It's only 4 milliseconds because the occupied bandwidth is 2.2 megahertz. Whereas groups 2 to 3 have an occupied bandwidth of 1.2 megahertz and the latency is 7.3 milliseconds. So there's a few different operating modes that you can put GLX-D in, one of which will be the most appropriate depending on your particular application and environment. So let's take a look at how GLX-D performs in multi-channel systems. So here, in this example, each transmitter requires 6 dedicated frequencies. So 3 transmitters will require 9 primary frequencies for transmission, plus we're going to have 9 additional frequencies for backups, 3 per channel. So for a 3-channel system, we're using 18 frequencies, including backups. Now, in the case of interference on one microphone's primary frequency, that microphone will shift to use one of its backup frequencies instead. However, we may find that in that environment, the backup frequencies that are assigned to that particular transmitter may not actually be the cleanest to use out of the whole system. It may be that one of the other backup frequencies assigned to a different microphone has a better signal-to-noise ratio and would have actually been the best frequency to deploy. So we've been thinking about this, and we wanted to improve the performance of GLX-D and maybe make the backup frequencies available to all transmitters in the system. So the answer to this was GLX-D Advanced. So by adding a UA846ZS frequency manager to the GLX-D 4R receivers, we now have what we refer to as a GLX-D Advanced system. The frequency manager provides improved RF performance. It allows for antenna distribution and seamless frequency management for up to 9 GLX-D Advanced rack mount systems in typical environments, or 11 under optimal conditions. So as you can see from this slide, one frequency manager can manage a system of 6 receivers, or we could link 2 frequency managers together to manage an 11-channel system if your RF environment is ideal. So let's talk a little bit more about the RF improvements that GLX-D Advanced offers. So without the frequency manager, GLX-D supports 4 channels typical, or a maximum of 8 under ideal conditions. Now, as we've just learned, standard GLX-D transmits 1 primary and 2 lots of repeat data sequentially across 3 different frequencies per channel. There are, therefore, periods of time when no audio is being transmitted on each of those carrier frequencies. So the frequency manager improves on the spectral efficiency by tightly synchronizing GLX-D 4R receivers to fill in those gaps. This synchronization enables multiple transmitters to share the primary frequencies of other channels to transmit their repeat data during the time slots when that frequency would have otherwise been unused. In the example presented here, we see the net result of a 3-channel system managed by a frequency manager. So we've got 3 systems transmitting on 3 primary frequencies, and that's including all of our repeat data. And the backup frequencies now become a shared pool instead of dedicated to each channel. So just to point this out so it's a bit clearer in what we're doing with the colors here, if you take transmitter 1, for example, which is blue, then it's transmitting its primary data in time slot 1 on frequency 1. But then for its repeat information on time slots 2 and 3, we're actually using frequency 2 and frequency 3, which are the primaries for transmitters 2 and 3. So you can see that now our table here is full. So we've removed all the gaps that we had with GLX-D. and the frequency manager is key to this. That's what allows us to have a few extra channels on air compared to GLX-D. And it also allows for the use of the best backup frequency possible as required, rather than only being limited to a couple of backup frequencies dedicated to your transmitter, depending on the group that you're using. Now, as far as the backup frequencies go, as I mentioned, the frequency manager is continuously scanning the environment to rank the quality of these, and it will dish out the best one. Okay, so let's move on now to talk about Microflex wireless. So as I mentioned at the start of the webinar, this system operates in the DECT frequency band. So the DECT range is either 1880 megahertz to 1900 or 1920 megahertz to 1930, depending on the country that you're in. Now, this is a key difference because you might have noticed that's a 20 megahertz range or a 10 megahertz range, depending on country, and that does have an impact on channel count with MXW. Systems that are in the 10 megahertz range, which the US is in that range, they have 5 carrier frequencies per DECT band. But in some other parts of the world, the DECT range is larger and they can have 10 carrier frequencies per band, which effectively doubles the channel count you can have with Microflex wireless. So that's just something to keep in mind. Now, some of the smart MXW technologies to enable reliable performance, again in this congested DECT range, include RF scanning and continuous spectrum monitoring by the APT, automatic frequency allocation, robust interference detection and avoidance processes, and we also have a frequency diversity transceiver design. So let's jump in now and take a look at each of those smart technologies. So the DECT range, like Wi-Fi, is commonly shared with other wireless devices, and in this range that includes things like cordless phones, walkie-talkies and consumer intercom. So like the 2.4 gig range, the potential for interference at 1.9 gigahertz is pretty high. For this reason, the MXW system features a scanning tool that surveys the RF spectrum for the presence of other DECT devices. It calculates the percentage of the DECT range that is occupied, providing current and peak percentages of RFI activity for up to a 24-hour scan time. On completion of a scan, the system presents a pie chart depicting the scan results, where low or no RFI is green, the presence of sort of moderate RFI is shown as yellow, and high RFI is shown as red. The system will then use this information to provide 2 channel count estimates, one conservative estimate and one more aggressive. Now, the aggressive estimate suggests a higher potential channel count, though the risk of interference in this mode is greater than the conservative estimate. So smart tools such as this really help engineers to assess the availability of the DECT range, and it does provide some guidance in terms of how many channels may be expected to work reliably in a given environment. Now, once an MXW system is installed, frequency coordination and deployment is completely automatic. MXW operates using both time and frequency information, similar to the way GLX-D does. But the MXW system divides time into frames that are 10 milliseconds long. And each frame is then divided into 24 time slots, each of which is approximately 417 microseconds long. As previously mentioned, there are either 5 or 10 carrier frequencies available to transmit on during each of these time slots, depending on the region that you're in. So the RSSI tables presented here are for a 5-carrier system, which is the standard in the US. The APT is able to sequentially receive audio from a different MXW microphone transmitting on a particular carrier during each of the 417 microsecond time slots. The APT manages the synchronization of all linked transmitters so they all know which time slots are theirs to transmit on and they don't interfere with one another. In terms of frequency allocation, MXW microphones and access points automatically select the best time slot frequency combination to use. So the RSSI tables in this slide demonstrate the process the system follows to make this determination. Each MXW microphone transceiver has an RSSI table of 24 time slots by the number of carrier frequencies available. So for the US example presented here, that nets us 120 possible time slot frequency combinations from which to choose from. In an MXW microphone, when it's first powered on, it has no information regarding the availability of any of these time slot frequency combinations. So in those first few seconds of power on, MXW microphone transceivers actually listen to the RF spectrum to sense occupied time slot frequency combinations. Then they automatically select available time slot frequency combinations to transmit on themselves. So the two RSSI tables shown here demonstrate this process. So the transmitter goes from having no information about the environment, which is the top table, to having a fully populated RSSI table in a matter of a few seconds after being powered on. And the colors represented there mean the same thing that we spoke about previously for the spectrum scan run by the APT. Now, when a linked MXW microphone transceiver is removed from a network charger, it's already time synchronized with the access point. The microphone then receives spectrum information from the access point itself, and it uses that information in combination with its own internal populated RSSI table to negotiate the best frequency time slot combinations to use with the APT. There's then a little handshake process between APT and microphone, after which time the microphone begins the transmission of AES-256 encrypted audio. Now, what's really, really impressive is that all of this is completely automatic. There is no input required from the end user. All you have to do is link the microphone to the APT by a simple button on the network charger, remove it from the slot, and all of this happens in the background. So very, very intelligent technology going on there. Now, I would like to talk a little bit about systems with multiple APTs. So, these are systems with more than 8 channels, for example. So it is essential that all APTs are synchronized as a single configuration. This enables multiple transmitters to share the same 5 or 10 carrier frequencies, but avoid interference by using them at different time slots across multiple time synchronized APTs in the config. So at a particular time slot, only one transmitter in the complete system will be using a particular carrier frequency, but this frequency may be reused by a different transmitter, even if it's linked to a different APT in the configuration, at a different time slot. Right? So this is pretty key. In multiple APT systems, we do run into interference problems, which in DECT-based systems are commonly referred to as, say, sliding errors or collisions, if the APTs are not precisely time synchronized. And remember that each of these time slots is only 417 microseconds long, right? So time synchronization needs to be very tight between multiple APTs. So consider the case of a transmission on carrier 1 at time slot 5. This would be effectively received by the linked APT, which is APT1 in this example. In a synchronized system, time slot 5 occurs at exactly the same time across all APTs in the configuration. All other APTs are aware that APT1 is receiving carrier 1 at time slot 5, so they automatically use a different carrier in this time slot to avoid generating interference. Without synchronization, though, time slot 5 may occur at different times on different APTs, right? So each APT in the configuration doesn't actually know if it's going to cause interference on the other APTs. That is the situation that's depicted in this slide. If this transmission on carrier 1 at time slot 5 on APT1 is interpreted as interference across multiple time slots on APT2. This is because the time slots are not synchronized and the two APTs cannot work together to manage the complete system. So that's one key reason why synchronization is very important. Here's another example. Transmission on any frequency at a particular time slot can actually generate some low-level spillover noise into adjacent carrier frequencies at that same particular time slot. Now, in synchronized systems, this noise is contained to just 2 adjacent frequencies of the identical time slot number, one on the carrier just above and one on the carrier just below the transmission frequency. Without system synchronization, though, if we don't have that precisely aligning time slots between all APTs in the config, this spillover noise can actually affect multiple time slots on the other APTs. And that is the situation represented here. Transmission on carrier frequency number 3 at time lot 6 on APT3 is generating low-level noise spill onto carriers 2 and 4 at multiple time slots on the other APTs. Now, the confusing thing is that sometimes I've seen integrators install MXW systems with multiple APTs and forget that they need to make a synchronized configuration. But because of the very intelligent technology integrated into Microflex Wireless, often the system can continue working flawlessly, and when these cases of interference occur, the system just moves away and uses different frequencies. So you can actually get away with not doing this, even though that's not best practice. The problem occurs when you have very high channel count systems, or you're in an environment that has a lot of other DECT activity. Eventually, the Microflex wireless system will run out of space to run away from its own internally generated interference, right? And these are the times when synchronization is absolutely critical, and it may turn around a system that you can't get working into a system that works flawlessly. Now, what I think is really smart about this is that just like everything else we've spoken about so far, the synchronization is an extremely complex technical process, but the user interface to configure it is very, very simple. So it's just set up in the GUI for an APT. You'll have a list of all your devices on the network, and you just set them up to be in the same configuration with a few sort of drop-down boxes in the GUI, and then everything else is managed behind the scenes. So extremely simple for someone who's really not too experienced with this system to set up a time-synchronized system with multiple APTs. Okay, we'll move on now to talk a little more about hardware in MXW. So MXW handheld transceivers feature diversity transmitters. So two orthogonal antennas exist on the MXW handheld microphone PCB. For anyone that's really interested in this, they may have taken one apart themselves and noticed this and wondered what they were for. Well, MXW handheld microphone signals are only ever transmitted on a signal frequency at any given instant, but the MXW transmitter determines which of these two antennas is the best one to use to transmit that signal. So these dual antennas are also designed for diversity reception of the MXW control data and the audio back channels. MXW access points also feature dual antennas, and the microphone is able to determine which antenna is polarized such that it will produce the strongest signal at the APT. Right, so the MXW system, its processing ensures that the optimal TX-RX antenna pair is always in operation. And for anyone that's familiar with polarization from UHF systems, it's a very similar thing here. And polarization mismatches can result in huge amounts of signal loss, up to 20 dB in a worst case. So for the system to automatically manage this in the background, it really gives you a very resilient, much more stable system. So very intelligent engineering on the hardware side there as well. Okay, so we're going to move on now to talk a little bit about our UHF-based systems. Well, predominantly UHF-based. So these include QLX-D, ULX-D, and Axion Digital. First up, I'd like to talk about the digital versus analog signal-to-noise requirements. So a key difference between analog and digital wireless systems is the way in which the audio responds to the RF carrier-to-noise ratio. Analog systems exhibit a fairly direct relationship between RF carrier-to-noise and the audio signal-to-noise ratio. So as the RF carrier-to-noise ratio degrades, so too does the audio signal-to-noise ratio. Digital systems do not exhibit this behavior. If a digital system is delivering error-free data, the audio is perfect. There is no transmission-induced noise in your demodulated audio. So that's a really key advantage of digital systems. In the presence of interference, of course, Shure's digital wireless systems will try to conceal the interference if it's not too severe. And at some point, though, they will simply mute if you've got strong interference. But what's nice is that it will mute without any clicks, pops, or other audible artifacts. So the chart that I'm showing in this slide indicates the point at which RF noise will cause ULX-D, for example, to mute, compared to the gradual degradation of audio signal-to-noise ratio and the eventual squelch point of two high-end analog wireless systems. So this is an indication of the robustness of Shure's smart digital modulation schemes compared to older generation FM systems. Now, by reading this slide, we can see that ULX-D can operate flawlessly at an RF carrier-to-noise ratio of only 13 dB. Now, most analog systems will squelch at carrier to noise levels where ULX-D is still delivering flawless audio. And remember that before you even get to the squelch point, you're slowly getting an ingress of noise into your demodulated audio with those FM systems. So really, this is a fantastic performance from ULX-D. Now, Axion Digital, which I'm not representing here, is better still. The digital modulation scheme is actually quite different to ULX-D. And operation is possible in Axion Digital with carrier-to-noise values as low as 3 dB. All right, so 3 dB, that is crazy. You've only got to be just a couple of dB above the noise floor for Axion Digital to deliver flawless audio with no noise whatsoever. All right, so even in some situations, it may even be possible to tune an Axion Digital transmitter right on top of a DTV station and still get that microphone signal working. So incredible engineering in terms of the modem that's used for these digital wireless systems. Moving on from that, we have another key benefit of these systems, and that is the option for high density mode. So a lot of people ask me, how does Shure actually achieve this? Well, at the most basic level, it comes down to carrier bandwidth. Now, digital systems like ULX-D and AD have a fixed bandwidth carrier. All right. Now, this is quite different to FM systems where the carrier bandwidth is not fixed. It sort of pumps in and out depending on the audio signal that you're modulating. So the consistent deviation of the digital carrier allows for precise characterization of the intermodulation products. Because of this, the ULX-D and AD receiver design emphasizes linearity over sensitivity. And when combined with some modifications to the modem, when high-density mode is enabled, these digital systems can achieve incredible spectral efficiency. So carrier spacing can be as little as 125 kilohertz apart, and transmitters may actually be tuned directly adjacent to each other without concern for problems with intermodulation distortion. Right, so you can stack up Axion Digital transmitters 125 kilohertz apart, just stack them right up. And for anyone that's familiar with sort of large channel count analog systems, there is no way that you could do that. Even if your carrier spacing was further apart, say 350 or 400 kilohertz, if you sequentially tuned transmitters in, like say at 400 kilohertz apart sequentially, you would have intermodulation products lighting up right on your carrier frequencies all over the place. You'd have huge problems with interference and most of your channels wouldn't work. But because of the really low carrier to noise ratios that these digital systems can operate at, you can do that. You do still get intermodulation products hitting your carrier frequencies, but the system can essentially ignore those and continue operating flawlessly. So that's how we end up with a spectrum scan like the one you see here, where you get over 100 channels or so in 13 megahertz. So fantastic performance from these digital systems. Now, some of you may be aware that transmitter power is limited to 1 milliwatt in ULX-D and 2 milliwatts in Axion Digital in high-density mode. But because of the significantly lower carrier-to-noise requirement, these low power settings in practice still achieve a system range similar to, say, UHFR operating at 10 milliwatts, for example. Right? So don't be too concerned about seeing the 2 milliwatt power setting in Axion Digital. You still get fantastic range out of that system because it is so much more efficient. Okay, interference detection in these UHF-based systems. It's a little bit different to GLX-D and MXW. So dual digital signal processors in AD and ULX-D receivers analyze the quality of the RF signal to predict the onset of interference. The receiver LCD is going to turn red, and it's going to display one of two possible warning messages when this happens. You'll have an interference alert or interference detected. Interference alert indicates low-level interference that's probably not going to be audible, and it might only cause a slight disruption to your audio signal. Interference detected is much more serious. It indicates a high level of interference that's deemed likely to disrupt your audio signal. So this is a very clear warning to the engineer to investigate a potential problem. Now, if you're using an Axion Digital system, retuning of the operating frequency to avoid interference may be either manual or automatic. Now, to introduce the concept of interference avoidance, we first need to talk about the AXT600 Spectrum Manager and ShowLink. So the AXT600 is a spectrum manager. It delivers wideband UHF spectrum scanning, spectrum analysis, and compatible frequency coordination. Scan data is used to calculate compatible operating and backup frequencies for all devices in your system. This compatible frequency list, or CFL as we call it, is constantly monitored and ranked by the spectrum manager based on the presence of noise and interference on those frequencies. The ShowLink network enables remote control of ADX transmitters via a 2.4 GHz Zigbee link. In systems containing one or multiple AXT610 ShowLink transceivers, the Spectrum Manager is going to manage automatic frequency deployment to both the AD receiver and the ADX transmitters via this 2.4 GHz data link in the presence of interference. In systems that have multiple ShowLink transceivers, something that's really cool is that network traffic and transmitter handoffs between multiple ShowLink access points is completely automatic and seamless to the end user. Now, Axion digital systems must include a Spectrum Manager and a ShowLink access point to enable interference avoidance, which may be configured in a couple of different settings. So you can turn it off completely if you don't want to avoid interference. You can set it to detect only, in which case the receiver will detect interference and display a warning message, but options for frequency changes will not be presented. If we set it to prompt, it's pretty much the same as detect only, but you will be then presented with a prompt for what you want to do in the case of interference, if you want to deploy a new frequency or ignore it, for example. And then there is a completely automatic setting, in which case a clear frequency will be automatically deployed to both receiver and transmitter. There are also a couple of settings to allow for customization of interference detection sensitivity. So normal, more sensitive, and less sensitive. These settings just adjust the how sensitive the process is. So less sensitive, for example, the response to interference at a low level, just below the audibility threshold. So interference detection is suppressed when the received signal strength is just below the exclusion threshold. We also have transmitter device IDs. So these can be used with these systems. So when you link transmitters to an AD receiver, for example, you can link multiple transmitters. And that's basically telling the receiver that these are the transmitters that I want to allow this receiver channel to demodulate. If then another Axion digital transmitter turns on, it has a different ID on that same carrier frequency, you'll get an alert from the receiver saying that this is an unexpected transmitter. So just another nice piece of technology to assist in managing your system. Okay, let's talk a little about frequency diversity. The term frequency diversity refers to the method by which the same signal is transmitted simultaneously on two separate frequencies to a single dual or quad channel receiver. So Axion digital and ULX-D receivers set to frequency diversity mode continuously analyze incoming signal quality using both signals to provide optimized audio on a single channel output. If RF interference or complete loss of one frequency occurs, the receiver automatically uses the other frequency to demodulate the audio. DSP-controlled routing between channels when interference occurs is seamless and, again, inaudible to the end user. Now, this can work with either diversity transmitters, ADX. So we have the ADX2FD frequency diversity. That contains two transmitters internally, so you can transmit the same microphone signal on two separate frequencies. Or you can also enable frequency diversity from dual belt packs. So if you want to double belt pack somebody, and this is pretty common in broadcast, for example, for a bit of redundancy, both on the pack, on the lavalier, and on the carrier frequency, then you can set that up as well with two belt packs. In theory, you could do the same thing with two handhelds, but it's not really practical to do that because they're going to be spaced apart and you're probably going to have issues with comb filtering. Okay, quadversity. This is a new technology that's been implemented in Axion Digital. Quadversity RF processing converts the AD4Q, so the quad receiver cascade outputs, into two additional sets of inputs labeled C and D, enabling the receiver to use 4 independent antennas and discrete RF signal paths to combine signals for a single microphone channel. This allows users to place sets of diversity antennas in different zones, or double the number of antennas deployed in a single zone to improve RF signal to noise in a challenging environment. So quadversity goes beyond simple antenna combining. It uses maximal ratio combining algorithms based on the signal quality of each input to optimize the overall received signal. Right, so performance is very similar to, say, Markov diversity with an AB antenna system, but we're now just doing that over 4 antennas. So in this example, well, in the previous example, we were looking at extending range between 2 rooms. So here we've got room 1, room 2, and we've got a diversity pair in each room. So this is useful if you want to cover, say, a stage and a backstage area from the one receiver without having to employ any sort of active or passive combining. In this example, we're deploying 4 receive antennas into one physical space to extend the range. Now, this is pretty important. I've seen lots of people come into problems where they might have multiple antennas like this in one space, but then they passively combine them. And they might passively combine them using something like a UA221. Now, the problem with that is that when you're combining antennas in the same space, they need to be electrically isolated from each other. If they're not, they will interact and they will form an array, and basically they're going to work as one virtual antenna. The problem with this is that the polar response of those antennas will change somewhat depending on how they're interacting electronically. So some people come into problems where they do this, they combine passively. Then when they walk test through a room, they might find some dead spots that, really when they're looking at the antennas and how they're positioned, they would expect full coverage there, right? And the reason for it is that by passively combining without isolating, you're generating an antenna array, and then you can have some problems with dead zones throughout the space. So quadversity solves this problem, all right, because all of these, what we're doing is like Markov diversity across those 4 antenna inputs. So that's a great application. Okay, finally, to close up the webinar, I just want to mention some of the software additions to help manage these UHF-based systems. So, of course, Wireless Workbench, which most of us would hopefully be familiar with. So this is a tool for system planning, frequency coordination, device control, and spectrum analysis. We've got frequency coordination and visualization tools to enable accurate calculation of compatible frequencies for the complete system. And of course, this includes products from third-party manufacturers as well. It's got monitoring and control features that allow for real-time adjustment of device and channel parameters of all of these network connectable UHF-based systems. Now, I'm not going to talk too much about Wireless Workbench as we have a lot of other training materials and videos on this, but I would like to point out a few of the key features just because they're really smart and they help us manage these systems. So, as I mentioned, the visualization tools are great to monitor the RF spectrum via plots and scans, and we also have analysis tools to assess frequency assignments and coordinate compatible frequency lists for deployment to system hardware. So the frequency coordination plot here displays selected scan data. You can throw up exclusion ranges, inclusion ranges as well, and you can put some frequency markers in there. Now, any Shure Network Connect receiver can be used as a scanner for scanning, or we can import scan files as well from third-party products like WinRadio scanners or TTI scanners, for example. The monitoring tab, this is great. It enables real-time monitoring and remote adjustment of network-connected devices. Parameters that can be adjusted at the channel strip are automatically updated on the hardware, right? So you don't have to then manually push these settings to the hardware. You make a change here in the software and it is automatically applied instantly on the hardware that you're looking at. So configurable receiver properties include radio parameters, audio parameters, most of the utilities and transmitter settings. Frequency, RF power, and network settings are also configurable for, say, PSM 1000 transmitters, for example. What else shall we mention? The timeline was a key addition in version 6.12. So this is a logging utility designed to capture key channel status information over time. The information recorded includes RF level, antenna status, audio levels, the presence of interference, ShowLink remote control status, and battery levels. So capturing and viewing the recorded data enables users to troubleshoot their systems. All right, so Wireless Workbench 6.12, it really helps wireless users better manage and monitor their UHF systems over the network, from pre-show planning right through to post-performance analysis. And finally, we've also got the Shure Plus Channels, which is a mobile app for Apple iOS devices, if you're not aware. This enables wireless monitoring and control of Shure RF systems. So monitoring functionality is freely downloadable, and mobile control of wireless channels can be added by an in-app purchase. Okay, so that's everything I wanted to cover today. That's a lot of very technical information in a short amount of time. But I hope it's been useful, and it gives everybody a greater understanding of the in-depth operation of the products. And I hope that that maybe there's been some key points there that jogged your memory with maybe some problems that you've had previously that you might now have a better idea of how to troubleshoot, or maybe some things to keep in mind for future installations. Now, I think there's a bit of time left, so if there are any questions, we can field those now.
Great. Thanks for all that information, Hayden. That was awesome. So far, I just have one question. So if you have any questions, type them in right away, and we'll get to them. And the first question is actually something that I can answer. This question is, in the future, will you have a high-end videography system replacing the UHF-R UR5? That's a really good question. Unfortunately, because we're a private company, we don't really discuss what we are working on or what we may or may not be releasing. But you can rest assured that we are always working to improve and expand our product lines to make them available to people that need to use them. So if there's something out there that might have a need, we might be working on it, but I can't really say one way or the other for sure. So that was one question. Any other questions out there? I'll give you a minute to type them in here. Not seeing. Oh, okay. Here we go. Okay. This question is, how many GLX-D transmitters can be used without frequency coordination issues?
Well, that is a tricky question because it is dependent on the environment as well. So, you'll see these settings of typical and ideal. So with GLX-D, we generally say that you can have a 4-channel system typical, right? And that's assuming that there is going to be a certain amount of other transmissions in the 2.4 gig range. So, a bit of Wi-Fi, for example. We're pretty confident that most of the time you'll get 4 channels working really well. But then you'll also have up to 8 channels under ideal conditions, right? So that's assuming that you've got no other Wi-Fi traffic at 2.4 gig. You've got clean spectrum to work with. You'll get 8 channels going. Now, if you wanted to add a frequency manager to that system and run GLX-D Advanced, because of the changes in the system, you can get higher channel counts. So I believe it's 11 channels under ideal conditions, and I think it's 8 or 9 expected most of the time. So if you've got some other Wi-Fi traffic with GLX-D Advanced with a frequency manager, you probably get 8 or 9 channels working quite well. And if there's really clean spectrum, 11 is the maximum.
Great. Okay, this next question is one I can answer. How do I get the mobile app? Well, as Hayden mentioned, it is iOS only. So if you are an iOS user, you can download it from the iTunes App Store for either your iOS device or your iPad. So that is how you get the Shure Plus Channels app. Next question is it possible that the RF power of GLX-D can be increased to 20 milliwatts or more?
I actually don't know. I don't believe so, but I could be wrong about that one. So, yeah, I would need to double check. I don't think so.
Okay. Next question. Other than Dante, what are the major differences between ULX-D and QLX-D?
There are some. Well, actually, in terms of audio and RF performance, they're very, very similar. You don't have high density mode on QLX-D, I don't believe. Need to double check that. But yeah. So you don't have that on QLX-D, but mostly it's the Dante interface. You also don't have the option for like a quad receiver or a dual receiver. I think it's a single channel only on QLX-D. So I'm probably missing a few things, but actually this is a good thing to point out. Shure have a really, really great FAQ section on our website. So you could just go into Google and type in Shure FAQ. That'll bring it up. And something like that is a really common thing. You could just type into the search box, differences between ULX-D and QLX-D, and it's all laid out there. So there is a huge database of Q&A on there. I refer to it myself all the time. And, if I wasn't on the spot at a webinar, I'd be looking it up right now so I could give a more accurate answer. But yeah, I think that's something to check. But yeah, the main things with QLX-D, I think, are the receiver channel counts, because it's just single channel for QLX-D, and the Dante connectivity.
Correct. Awesome. And you brought up the FAQ, which is a great resource. And if you don't find what you're looking for in the FAQ, and if we don't get to your question today, which it appears we're going to run out of time before I get through all of these because they're coming in fast and furious, you can send your questions to our team at support@shure.com. We have a great team of applications engineers that are manning the phones and manning that email channel, support@shure.com, and you can ask them just about anything. They are super smart. I know I go to them all the time. Okay, next question. Can GLX-D be managed by Wireless Workbench and coordinated with other wireless products?
No. So that's not quite how GLX-D works. Like, all of the frequency coordination in GLX-D is automatic within the system itself. So Wireless Workbench is really based around the UHF-based products. So things like QLX-D, ULX-D, Axient, and PSM 1000, plus a whole host of other third-party devices. So no, the setup of GLX-D is all completely automatic in the system itself. It does that itself.
Great. Okay, just time for maybe one or two more. So you spoke about groups 1, 2, and 3 on GLX-D. What about group 4?
Yeah, I think group 4 was a new group that was added in the I forget the firmware revision, one of the latest firmware revisions, where I think it's a one-channel group with a massive amount of backup frequencies. So if you've got a single channel GLX-D of GLX-D and you want that to be as robust and stable as possible, group 4 is the one to use, because you've got heaps of backup frequencies available. But yeah, you need to check the firmware revision that you're on for that. And make sure that it's the latest firmware revision to get group 4.
Fantastic. All right. Unfortunately, we are out of time and we have a bunch of questions we didn't get to. So if we didn't get to you, I severely apologize. But please feel free to send that question to us at support@shure.com. And as I said, our applications team can help you out. So that wraps up our first session of the webinar today. We hope you learned a lot, and we hope to see you on the next one. Have a great day, everybody.
Thanks, guys.